Hey guys, welcome back to my channel. So in this lecture we will be studying about heat transfer in buildings. So heat transfer happens due to three reasons, that is conduction, convection and radiation. So we all might know the basics, but let's just brush up through it. So conduction is the transfer of heat or electric current from one substance to another by direct contact. So if you directly come into the contact with the substance, the heat transfer is known as conduction. And convection is transfer of heat through a fluid, that is liquid or gas, caused by molecular motion, that is boiling of water, or that kind of heat transfer is convection. And radiation is the energy that is radiated or transmitted in the form of rays or waves or particles. So you, in a cold winter morning, you sit near a fired place, so the heat transfer takes place, that is radiation. Okay, so heat transfer happens due to conduction, convection and radiation. So talking about total heat flow. So heat flow is a combination of two things, that is sensible heat and latent heat. So sensible heat can be defined as heat transfer which involves change in temperature, while latent heat involves change in humidity. Okay, so total heat flow is sensible heat plus latent heat, and sensible is change in temperature, while latent heat is change in humidity. Okay, and talking about heat transfer in buildings, we saw that it happens due to conduction, convection and radiation. So for example, in convection, warm air rises and transfer heat to the ceiling. So as we know that warm air which is lighter, so it rises up and transfer the heat to the ceiling, while in conduction, heat is transferred from warm section of the walls and ceiling to the cooler sections. So just remember, energy always flows from high pressure area to low pressure area. That's why heat is transferred from high temperature area to a cooler temperature area. Okay, so that is low temperature area. So from outside to inside, okay, that is through the walls, which includes conduction. And radiation is heat is transmitted from the roof to the ceiling, from the roof to the ceiling in forms of waves. It's known as radiation. Okay, so conduction, convection, radiation in a typical building. So before going into details, let's understand few terms. Okay, that is the thermal property of materials, right? So first one is thermal conductance, also known as transmittance. So suppose you have a wall material and sun rays are falling into it. Okay, so what that material will do, it will absorb some part of it, it will reflect and it will transmit, right? So it is included with it will absorb, it will reflect, plus it will transmit. So if you have a wall and hot sun rays are falling on that wall, some part will get absorbed by the wall, some part will get reflected and some part will be transmitted, right? So conductance is the heat flow per unit area of a material with respect to its thickness. So consider this wall has a thickness like L, call it L. Okay, so and it will have a specific area also. So conductance is the heat flow which happens due to direct contact, right? And heat flow per unit area of the material. So per unit area of this wall with respect to its thickness is known as conductance. Okay, so the conductance is denoted by U, right? And its unit is heat. Heat is an energy, that is watt. So watt is joules per second. Okay, just remember this. Watt is joules per second. Okay, so the unit says watt per meter square area per degree change in temperature. Okay, so this can be either in Celsius or in Kelvin. So it is heat transfer in watt divided by meter square. Okay, that's the area, and per degree Celsius or Kelvin, that's the unit. Okay, so in imperial units is BTU stands for British thermal units per hour. So it is always British thermal unit per hour, and meter is changed to feet, and same happens with degree Celsius changes to Kelvin, right? So this is U value, that is thermal conductance. Now talking about thermal conductivity. Okay, so thermal conductivity defines rate at which the heat will flow through the material. So suppose for example I have a thin wall and a thick wall. Okay, so both has same solar radiation falling on it, but the heat transfer here will be faster, and here in the case of the fat wall it will be slower, right? So the rate of heat flow here it is higher and here it is less. Here it is more and here it is less, which means thermal conductivity of this thin wall is higher and thermal conductivity of this fat wall is lower. Okay, it depends on the thickness of the material. So since it is only a function of its thickness, so the unit becomes W divided by meter degree Celsius. It is not a square. Okay, it's just a function of thickness. Function of thickness means it depends on thickness only. Okay, so the same goes for British thermal unit per hour, feet, and Fahrenheit. Okay, so taking the units into consideration, we can infer that conductance is equal to conductivity divided by length. So we know that conductance is W per meter square degree Celsius is equal to conductivity, that is W per meter degree Celsius divided by length, that is W. So this M goes here and becomes meter square. Okay, so this is conductance U and this term is conductivity K. Conductivity is denoted by small k. Okay, so just try to remember and play with the units, and you will get the terms cleared. And the next term is thermal resistance. Okay, so if I have a wall, uh, like a simple brick wall, okay, and then I have a wall, simple brick wall, simple sandwiched brick wall with some insulating material in between. Okay, we all know what insulator is. So it delays the heat transfer. Okay, so here resistance of this wall is less. Okay, and resistance of this wall is high, which means heat will get transferred easily in this wall and heat will take more time to get transferred in this wall, which means its resistance is high and its resistance is low. Okay, so thermal resistance defines the resistance of a material to heat flow, that is how good a material is as a insulator. Okay, so R is given by 1 by U. Okay, it's the reciprocal of thermal conductance. So talking about thermal mass, ability of a material to store heat per unit volume. Okay, now to understand thermal mass, suppose I have a house. Okay, suppose, sorry for the bad sketch. So suppose I have a house which has a concrete floor. Okay, okay, concrete floor, and it has a high thermal mass. Okay, it has high thermal mass. So and I live in a region like hot and dry climate where the daytime temperatures are very high and the nighttime temperatures are very low, which means there is high diurnal variation. Okay, so diurnal variation is the difference between daytime temperature and nighttime temperature. Okay, so what will this thermal mass do is, when the solar radiation is falling on this material, falling on this floor, what it will do is, if it has high thermal mass, it will absorb more and more heat. Okay, so during the daytime it will absorb heat. Okay, and when the sun sets down, there is a temperature difference, and then this stored heat is released inside. Okay, so at night time when the temperatures are extremely low, we get heat out of it. Okay, so this is how thermal mass works. So thermal mass is the ability of a material to store heat per unit volume. Per unit volume. Okay. The greater the thermal capacity of the material, the more the heat it can store in a given volume per degree of temperature increase. So how good a thermal mass is? It depends on a material and greater thermal capacity, which means it is a good thermal mass. Okay. And the fifth and the last term is the time lag or thermal lag. So for example, again I have a thin wall and a thick wall. Okay. So solar radiation is falling on these two walls. What it'll do is it's absorb heat and radiate the heat inside. So for example, if it is the heat is falling at 9:30 a.m. Okay, and now it will radiate the heat inside for about say 10:30 a.m. Okay, so lag, the thermal lag is like 1 hour, right, in thin walls. But in the thick walls, if the heat is falling at 9:30 a.m., it will take more time to radiate inside because of its thickness. So like say it takes about 12:30 p.m., right? So the difference is for 3 hours. Okay, so 3 hours. So it has high thermal lag. The thermal lag is the delay in the heat transfer. Okay, so delay in the flow of heat energy from one side of the envelope to the other is known as thermal lag. Okay, I hope you got the concept. So first we saw conductance, that is W per meter square degree Celsius. Okay, U value, ability of conducting heat. Okay, and the second is conductivity, is the rate of flow of heat, which depends on its thickness, single function thickness. Okay, so its unit. So thermal resistance is reciprocal of conductance, so its unit becomes meter square degree Celsius by W. Okay, and there is one more term known as resistivity. Okay, so its unit is meter degree Celsius by W. Like we got conductance, conductivity, there is resistance and resistivity. Okay, so this is resistivity, and then we have thermal mass and thermal lag. Okay, so now looking into this small differentiation. So specific heat is the amount of heat required to raise the temperature of a unit mass by 1 degree Celsius. Okay, so for example, I have water body, okay, whose specific heat is 4.2, and I have wooden log, okay, wooden log, some grains with it, and it has a thorough specific heat of I guess 1.2 or something. Okay, so it has high specific heat value, water, and wood has a comparatively lower specific heat value, which means that the amount of heat energy required to change its degree temperature by 1 degree, okay, it's more. So when more heat falls on this water, then only the temperature will change by 1 degree. But in wood, if comparatively less heat falls, okay, then also its temperature will change by 1 degree, which means water has a better property against heat than wood. Okay, it's obvious, no? And more heat is required to change its surface temperature. But in wood, it can quickly change its temperature. That is why water bodies are preferred in regions of hot climate, right? Because they can store heat and radiate afterwards. So that is what specific heat means. And then comes density. So density is ratio of mass per unit volume, that's kilogram per meter cube, you all know that. And conductivity is, we saw the flow, rate of transfer of heat, and resistivity is the reciprocal of thermal conductivity. High resistivity means slow heat flow. You know, conductivity, resistivity, it's completely different, opposite I should say. And talking about thermal mass units is kilojoules per Kelvin meter cube. Okay, it's specific heat into density. So that is equal to thermal mass. Okay. So now remember what is equal to joules per second. We'll look into such units later. Okay. So now while calculating the U value of an particular wall, we can only add its R value. Okay. So now let's solve it with an example. So this is example 1. Okay. This part is example 1. Okay. So what I told you is for finding U value, we can add only its reciprocals. Like in this example, we got many surfaces like RSI, R1, R2, R3, R4 and RSO. Okay, so we for finding the total U value, you just cannot add U1 plus U2 plus U3. No, this is wrong. Okay, what you have to do is for finding this, first you have to find the resistance is 1 upon R1 plus 1 upon R2 plus 1 upon R3. Okay, so U value, you can never add or subtract U value. You can only add or subtract the R value. Okay, so that is how U value is calculated for a particular wall. High U value, which means high conductance, low resistance. Okay, and the U value is the inverse sum of resistance for each building material surface. It's the same text written what I told. So taking an example for instance, okay, now here I have an three wall materials, that is external plaster, hollow bricks and internal plaster, okay, whose thickness is given in meter, right, and conductivity is given in watt per meter Kelvin. Okay, what we have to find is conductance and resistance. Okay, now there are three materials, right, external plaster, hollow bricks and internal plaster. So for finding the U value, we have to add the R value, right? So U value of wall, total wall will be uh, U value of external plaster plus U value of hollow bricks plus U value of internal plaster. But we cannot add U value, which means 1 upon R value of external plaster plus 1 upon R value of hollow bricks plus 1 upon R value of internal plaster. So this will be the formula, right? So now we know that resistance is equal to thickness divided by K. Okay, so resistance is meter square degree Celsius by W. Thickness is meter and this is watt per meter Kelvin or degree Celsius. Here degree Celsius or Kelvin doesn't really matter. Okay, it ultimately defines temperature. So you need not convert a degree Celsius into temperature. Okay, sorry, degree Celsius into Kelvin or something. So this becomes meter square divided by meter square Kelvin divided by watt. Okay, so this is the formula for, so resistance is equal to thickness divided by conductivity. So solving for the external plaster, what we'll get as resistance is thickness 0.02 divided by 1.2. Similarly for hollow bricks it will be 0.2 divided by 0.9, and for internal plaster it's 0.03 divided by 1.2. Okay, so the values will be 0.016, 0.22, 0.025, right? So these are the resistance values. So resistance value is this one. So adding the reciprocal Adding the resistance values reciprocal, we can get the total U value, right? That is the conductance. So U is equal to 1 upon R external plaster, that is 1 upon 0.016 plus 1 divided by 0.22 plus 1 divided by 0.025. So solving this expression will give you the total U value. Okay. So what you have to do, if you have to find the individual U value, just do the reciprocal. So these are the three U values of external plaster, hollow bricks and internal plaster. So now here I have an example. Okay, you can try practicing this one for understanding conductance and resistance better. Okay. So till now we saw what thermal conductance is, what resistance is, what conductivity, resistivity, and then we saw specific heat, what is thermal mass, time lag, everything. We saw various terms. Okay. So now let's just solve an basic example. Okay. So we saw conductance. Okay. That is U. And now in this problem we will be solving heat transfer due to conductance. So heat transfer is area into U value into the temperature difference between inside and outside. So this is the heat transfer due to conductance Q. Okay. So let's just read the question. A 4 meter into 5 meter wall consists of 3 glass windows of 1.5 into 1 meter dimensions. Okay. So I have a wall. Okay. Here the dimensions are 5 meter into 4 meter. Okay. And I have 3 glass windows of 1.5 into 1 meter each. So 1 meter and this is 1.5 meter. I have 3 windows. The wall thickness is 0.125 meter. Okay, this is the wall thickness with a thermal conductivity of 0.5 watt per meter Kelvin. So thermal conductivity of wall is 0.5 watt per meter Kelvin. Okay, while the glass windows are 6 mm thick with a thermal conductivity of, so K value of glass, it's 1.24, okay, watt per meter Kelvin, and thickness is 6 mm. Okay, and the values of internal and external surface conductance of the wall, here it is U value. Okay, external surface conductance and the internal. So internal U value is 8.3. Okay, U internal it is 8.3. I'm not writing the units, it's watt per meter square Kelvin, and external U value is 34.4. Okay, the internal and the external temperatures are 21 degrees Celsius and 30 degrees Celsius. So internal is 21 degrees Celsius and external is TO outside. Okay, it's 30 degrees Celsius, 21 and 30. So respectively, calculate the total heat transfer rate through the wall. What percentage of heat transfer is through the windows? So I have to find the total heat transfer. Heat transfer is given by Q. Okay, Q is for heat transfer, U is for conductance. What percentage of heat transfer is through the windows? Okay, now to solve this problem, first we have to do is properly just identify what terms are what and just apply in the formula, that is Q is equal to area into U into temperature difference. Okay. Now we know that U value of wall is what? Its conductivity divided by its thickness, right? We saw in that earlier formula conductance is equal to conductivity divided by thickness. So it's 0.5 divided by 0.125, right? Which will give me 4 watt per meter square Kelvin. Okay, similarly, uh, so now we have this. Instead of going for this, there is another simple way through which you guys will understand it better, right? Now the basic formula is total heat transfer is equal to A into U into delta T, right? Area A is the area. So for total heat transfer, it will be Q of windows plus Q of wall, right? So for Q of windows, finding the Q value of windows, we have to find the U value of windows first. Okay, then U value of walls, and then we just have to add them. That is AU delta T of this one and AU delta T of this one, right? I'm just separating the formulas. Okay, so now for finding the U value of window, okay, what you have to do is, or U value of glass, whatever it is. So first, the thickness is given as 0.6 mm, that is 0.006, right? Divided by, we know that resistance is equal to resistance is equal to thickness divided by K, right? Using this formula here, thickness divided by conductivity is given as 1.24, right? And then we have the two terms, internal U value and external U value. U value is given, but we cannot add U values, which means we have to take the reciprocal. Okay, which means we are taking the resistance value to add, right? Let me just put my phone in silent. So this is total U value of window. Similarly, U value of wall. Okay, try to frame the equation. Just pause the video and try to frame the equation. Okay, so the U value of wall will be thickness of the wall divided by its conductivity, that is 0.5, plus the internal and the external U values resistance. Okay, this will be the same. Okay, so the solving these equations, we get U value of window, U value of wall. Okay, we know the area of window, that is 3 windows into 1.5 into 1, that is the area of windows, right? And the area of walls is, do the complete area, that is 5 into 4. Okay, that is 20 meter square minus this area, minus window area will give me the wall area. Okay, so now we have area, this one, all the four terms we have. Now delta T. Delta T is the temperature difference between inside and outside. Okay, so that is 21 degree and 30 degree. Okay, so what's the temperature difference? Okay, you cannot say 21 minus 30, that is wrong, or you cannot say 30 minus 21, both are wrong. Okay, we just have to see the magnitude difference. Okay, so here the magnitude difference, that is inside plus outside. Okay, it's always Ti minus To. Okay, so it's 21 minus 30. Okay, but it ultimately becomes plus. Okay, it's just the temperature. We need not consider sign, that is minus or plus. It just indicates the direction of heat flow. Okay, we just have to see the magnitude difference or the magnitude addition. Okay, so here it is 51. So delta T is 51 degrees Celsius. Okay, now we have all the six terms in this equation. So substituting all this value in this equation, you will get the total heat transfer. Okay, and the second question is what percentage of heat transfer it takes place through windows. So just take these three terms. Okay, this is heat transfer through windows. So divide these terms by total heat transfer and multiplying it by 100 will give you the percentage. So total heat transfer through percentage of heat transfer, it is Q value of window divided by Q value of total into 100. Okay. I know it's a bit heavy for a first introductory lecture, but we'll solve few problems. Okay, so you don't worry and keep on practicing. I'll end this session here. So what we saw in this session was we saw how heat transfer takes place in buildings, that is conduction, convection and radiation. Okay, then we saw basic formulae or basic terms instead: conductance, conductivity, resistivity, resistance, mass and thermal lag. Then we saw the difference between various terms. Then we saw U value is addition of R value. We cannot add or subtract U value, but we just can add and subtract only R values. Okay, here 1 upon R because resistance is the reciprocal of U value. Then we saw how to find conductance and resistance. Okay, and then the basic example problem. Try to solve this. If any doubt, put up in the comment section or we'll solve many more problems also. Okay, so thank you guys, keep on preparing, take care.